Hi class. In this lecture here we want to continue talking about applications of differentiation by talking about two theorems. The first one's going to be called Rolle's theorem and the second one's going to be called the medium value theorem. Alright, so all we're going to do in this section is we're going to understand, I'll describe what Rolle's theorem is and then we'll use it, and then we'll do the same thing with the mean value theorem. And this lecture is actually going to be on the little bit on the shorter side. It's really just introducing the theorems. These are two what we call existence theorems that they tell you that something exists. And then I just want to work just some real brief application problems with it. Okay, so here's the first one. Here's Rolle's theorem. Let's let f be continuous on some closed interval from a to b, and it's differentiable on the open interval from a to b. Now, if f of a is equal to f of b, okay, so what that means is, I'm going to do the visual of this so you can see. If you have some function here, okay, here's a, here's b, and these two values, f evaluated at a and f evaluated at b, are equal, okay? As long as the function is continuous on this closed interval, okay, or on this closed interval from a to b, then there is at least one number c that's going to exist between a and b, such that f prime of c is equal to 0. Because if these two values are equal and the function is continuous, there's no way you can draw it such that there isn't a turning point here. And even if you draw like just a horizontal line, well then f prime evaluated at any value would be equal to 0. So the only way that you can have this is if the two a and b are equal, okay, they have to be equal, then there has to be either a relative max or relative min here. Otherwise, it's a horizontal line. So that's basically what Rolle's theorem is telling us. All right, so let's do a quick example here. So let's determine whether Rolle's theorem can be applied to f of x on the closed interval from a to b. And if Rolle's theorem can be applied, find all values of c in the open interval a to b such that f prime of c is equal to 0. And if the theorem cannot be applied, explain why. Okay, so for this one here, the first thing you have to do is we'll look at the function. F of x is equal to x squared minus 8x plus 6 on the interval from 2 to 6. What needs to happen, this is my a and b here. What needs to happen is f of a has to equal f of b. So the first thing I'm going to do is I'm going to take this the end points of the interval and plug it into your function. So this would be 2 squared minus 8 times 2 plus 6. I'll just help out a little bit. This is going to be negative 7 just to save some time. And then f of 6, you're going to get the same thing. This is 6 squared minus 8 times 6 plus 6. This is also going to be negative 7. Okay, since this f of 2 is equal to f of 6 here, and the function is continuous on the interval, on this 2 to 6, we can apply Rolle's theorem. And if you find first the derivative here, f prime of x, that's going to be 2x minus 8. What the theorem says, well, there has to be some value in this interval such that the derivative is equal to 0. So if you set this equal to 0 and solve, look, you can see that 4 falls in the interval, and yeah, because the two endpoints were equal, okay, there was a value between 2 and 6, 4, where the derivative equals 0. That's what we're seeing here with when we apply the theorem here. So now the second one here, the first thing you're going to do is you're going to check the endpoints, right? So we have f of x is equal to x to the 2/3 power minus 1 from negative 8 to 8. So this would be negative 8 to the 2/3 power minus 1, which ends up being 3, right? You do the third root of negative 8 is negative 2, squared is 4, minus 1 gets you 3, and then it's the same deal with 8. But when you go to take the derivative here, right, f prime of x, okay, you end up getting 2/3 x to the minus 1/3, which is 2 over 3 times the third root of x, right? And so you have to ask yourself, okay, what if you look back at the theorem, okay, it has to be differentiable on the open interval from a to b. But if you look here, it's not differentiable at 0, okay, which is in the interval. So not differentiable at x is equal to 0, which is in the interval. From -8 to 8. Right? So what that means is, for this example here, you cannot apply the theorem. Okay. Dun, dun, dun. So that's Rolle's theorem. Let's now talk about the median value theorem, or the mean value theorem. Okay. So if f is continuous on a closed interval from a to b, and again differentiable on the open interval from a to b, then there must exist some number c in that interval a to b, such that f prime of c is equal to f of b minus f of a divided by b minus a. Okay. So the mean on the mean value theorem refers to the mean or average rate of change of f over the interval from a to b. So what the mean value theorem says, look, if you look at the average rate of change of f from a to b, there has to be, okay, at least one c, such that the derivative evaluated at that c is equal to the average rate of change. Okay, that's all that means with this mean value theorem. And what I'm going to do is I'm going to show you this example here, and we're going to use our graphing calculator a little bit. And hopefully, what it's going to do is show you, the mean value theorem in practice, so that you'll see that it works here. Okay, so let's consider this graph here. So we got the graph of the function f of x is equal to x squared minus x minus 12. Okay, we have this. This is what the graph looks like, and we want to do the following things. First thing we want to do is we want to find the equation of the secant line, okay, joining the points -2, -6, 2, 4, 0. And so what this secant line is going to do, okay, that's going to be the slope here, okay, and what the slope of this secant line is going to be what's called the average rate of change of this graph, okay. Then we're going to use the mean value theorem to determine a point C that's somewhere between -2 and 4, such that the tangent line at C is parallel to the secant line. Okay. And then we're going to find an equation of the tangent line through C. And then what we're going to do is, then you're going to see, and it's going to be really cool, we're going to use a graphing utility to graph the function. Graph f of x, the secant line, and then the tangent line, and you're going to see something really, really cool. Okay, so first thing we're going to do, all right, we're going to find the equation of the secant line, and this is what the secant line is going to look like, okay? Okay, this is going to be the secant line through these points. And what's real, I just want to note here what's really important, the slope of this line gives the average rate of change of our function from x is equal -2 to x is equal 4. All right, so the first thing you're going to need to do, all right, we'll do this here, is we have our 2 points, right? So just to go back, our 2 points were -2, 6, and 4, 0. -2, -6, excuse me. So if you want to find the equation of the line, the first thing you need is the slope, right? Slope is change in y over change in x. So this ends up being 6 over 6, or just 1. So then what you can do here, right, to find the equation of the secant line, you're just going to use the point slope form, right? And I'm just going to use this one here. So it's y minus 0 is equal to a slope 1 times x minus 4, excuse me. So this is y is equal to x minus 4. Okay, that's going to be the excuse me, the slope of this, or the equation of this secant line right here. Okay, so now what you're gonna do is you're gonna use the mean value theorem to determine a point C in the interval from -2 to 4, such that the tangent line at C is parallel to the secant line. So what's important here is parallel lines have the same slope. So you're gonna find f prime of x. Well, f prime of x here is just 2x minus 1. And so then what you're going to do is you're going to say, okay, I want the slope of the tangent line to have the same slope as this line over here. So you're going to set this equal to 1, and you're just going to solve. So you're going to be left with 2x is equal to 2, and you're going to get x is equal to 1. So here's what I'm saying. I'm saying here, okay, I use the mean value theorem here to say, look, when x is equal to 1, the slope of the tangent line is going to have the same slope as the secant line, or it's going to have the same slope of the average rate of change of the graph from -2 to 4. All right, so find an equation of the line here. Okay, well, you got the slope. Okay, the slope is going to be f prime, right, evaluated at 1, which you know is just 1 because we just solved it, equal to 1. And then to find the point, you're going to need 1 f of 1. Right? Well, if you plug 1 into our original graph here, our original equation, you get 1 minus 1 minus 12. So you get the point 1 comma negative 12. And so here, you're going to use your point slope again. So you're going to get y minus 12 is equal to 1 times x minus 1, or y plus 12 is equal to x minus 1. Subtract the 12 over, and you get this. Now you're going to see something really, 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 really cool here. And I'm going to load up my graphing calculator now so you can see it. So when I load up my graphing calculator here, here's what I want to do. I want to plug in first the original function. Okay. So when I do that, just so you can see, here's the graph. It's the same graph as this. Now let me plug in the secant line, all right? The equation we got for the secant line. So right on top, so this is just y is equal to x minus 4. And you can see the secant line. I'll even zoom out a little. Now watch this, okay? The slope of this line gives the average rate of change of the graph from this point to this point here. So now when I plug in, all right, this equation of the tangent line at x is equal to 1, so this was just x minus 13. Look here. You can see here I found that there is a point, okay? A point in that interval, okay, in that interval from -2 to 4, where the average rate of change was the same as the slope of the derivative, or the slope of the tangent line at some point. And you can see it. You can see it literally right there. All right, so let's do. So we've gotten this problem here. Let's do one last problem talking about the mean value theorem here. Okay. So this one here, it's what it says is determine whether the mean value theorem can be applied to f of x on this closed interval. And if the mean value theorem can be applied, find all values of c in the open interval a to b such that, okay, the mean value theorem here holds, okay? And then if the mean value theorem cannot be applied, let's explain why not. Okay, so let's just go back and look at the mean value theorem here, okay? If f is continuous on the closed interval, okay, and differentiable on the open interval, then let's see if we can find a c such that the average rate of change is equal to the slope of the tangent line at that value c. Okay, so I want to see if the mean value theorem can be applied here. Okay, so f of x is equal to x cubed plus 2x, and this is from -1 to 1. And look, this function, when I differentiate it, right, I get 3x squared plus 2. Look, this function is continuous and differentiable on this interval. Okay, you can look at the derivative. The derivative exists on this interval. So we're good. So let's find this average rate of change then, okay? So I've got to find the points here, okay? So the first point I'm going to use is going to be -1 f of -1. All right, well, if you plug -1 into this function here, okay, you're going to get -1 plus, or -1 cubed plus 2 times -1. You end up getting -3. And then I'm going to plug this point in. 1 f of 1. Plug x into that. You're going to get 1 plus 2. You can see this is 1 comma 3. All right, so let's find this f of b minus f of a over b minus a. Okay, so it's literally going to be f of 1 minus f of minus 1 divided by 1 minus minus 1. So this becomes 3 minus minus 3 all over 1 plus 1, which is 6 over 2, which is 3. So now let's see here if if we can find a c in -1 to 1 such that the average rate of change is the same as the slope of the tangent line. So I'm going to take my derivative. (3x squared plus 2) and set it equal to 3 here. I'm going to subtract 2 over, divide by 3, and I'm going to take the square root to solve. And look, it turns out you get 2 solutions here, okay? This, you get plus 1 over the square root of 3 and minus the 1 over the square root of 3. And both of those are in the interval here, okay? So it's like, boom, yes, it actually occurred twice. So we see here then that f of -1 over the square root of 3 is equal to f of 1 over the square root of 3, which is equal to 3 here. And that's the average rate of change of that function from -1 to 1. All right, and then finally, just this next one. Can we apply the mean value theorem here? And so let's just look back. Like, what does it say? F is continuous on this closed interval. So if I look at this function here, all right, is f continuous on this closed interval from -3 to 3? No, it's not. So you can't apply the mean value theorem here. All right, and this is just because f of x is not continuous at x is equal to 1, which is in the interval from -3 to 3. Okay, class. And I know this was just a quick introduction to these two theorems, and I just wanted to provide the introduction to it. We're not going to spend too much time on these theorems. You'll get you'll get a question on it on your homework on each of these, but it'll just be like what I've done here. And just we've seen them, and we'll know them when we see them in future lectures now. Okay, class. Let me know if you have any questions.